Welcome you all to the second day of the summer school. Uh, Professor Prajakta will continue with minimum mix span.
Can everyone see this font? Okay.
Black.
Is black better? Okay. Yeah, so we will look at the minimum make span problem, or what is called as job scheduling. So the input is a set J of n jobs and a set M of M machines. Because our goal is to schedule these jobs on these machines. Each job needs to be scheduled only on one machine in a contiguous time slot. So you can't execute a job halfway, then put it aside and execute something else. And there is a processing time associated with each job machine pair. Okay, so processing time Pij for job I on machine J. So this Pij is given to you for every I in the set J and every J in the set. So the goal is to assign each job to exactly one machine. Depending on which machine it is assigned to, the time of the job will be decided. So for an assignment, let me call the assignment F of jobs to machine. This is of course a function because every job gets assigned to exactly one machine. We define make span of this assignment to be maximum over all machines sum over the processing times of the jobs which are assigned to that machine. That is, in simple words, it is maximum amount of time taken by any machine to finish the assigned jobs. Any question about the problem setup?
Are the number of machines greater than the number of jobs? Or because
We will typically assume that the number of jobs is much more than the number of machines. So a machine can get many jobs, but we can assign one job to only one machine. So if we kind of draw a graph of time versus machines, and then an assignment would look like this. So this is the time taken by one job on one machine, and this is another one. So this is for one machine, and there are m such machines. And a machine might, different machines will finish at different times. So here the make span will be determined by the machine which finishes last. So this interval is our make span. So each machine can execute only one job at any point of time, but whatever jobs get assigned to it, it will finish them one after another. So it will take summation Pij amount of time, where I only refers to those jobs which are assigned to that particular machine. So yesterday you have seen how to use linear programs for Vertex cover problem. So now here also we will use linear program. So first of all we should cast this problem as a linear program. So I would encourage you to think and come up with some suggestions about how we can write it. So there are three components that a linear program needs. There is an objective function, there are constraints, there is a set of constraints, and one needs to decide the variables. Typically variables is the simplest thing to decide on. Exactly. So the set of variables would be xij. So we always write integer program first and then remove the integrality constraint, because that constraint makes the problem hard. So variables xij, where I is a job and j is a machine. The interpretation is that xij is 1 if I is assigned to j, and 0 otherwise. Of course we cannot insist on having a 0-1 solution, but we will have this interpretation in mind while writing our constraints. So how do we write our constraints now?
If you take a single I and sum over all j's, it should be exactly 1.
Yes, so every job should get assigned to exactly one machine. So that will give us the constraint summation over xij, where j goes from 1 to m, is exactly 1, and this is true for every job. Okay, so again, what does this constraint say? We are summing over machines fixing an I. So this sums xij variables over all machines for a particular job I, and hence it should be exactly 1, because every job should get assigned to only one machine. So that xij variable will be 1, the rest will be zeros, and that will make this sum. Now we have to decide what our objective function is, what other constraints are. The objective function intuitively should be the make span, and we will just have a variable for make span. So apart from these xij variables, we will have variable lambda denoting the make span value. So we want to minimize this lambda. So minimize lambda such that this happens, and now we can write the second constraint which corresponds to the make span constraint. So since lambda is the make span, every machine should finish its assigned jobs within lambda, then only it will be a valid make span. So we will have a constraint for that. So sum over I equal to 1 to n xij. Now when we are summing over I to n for a particular j, this will refer to jobs which are assigned to a particular machine j, but then this xij will be only a 0, 1 value. But if job I is assigned to machine j, there is going to be a pij amount of time taken for that. So we have to multiply with pij. What should the right side of the constraint be? Less than equal to lambda, and this should be true for every machine. Please let me know if the LP itself is not clear. I will clarify that. If you are not comfortable with having a variable on the right side, you can of course write this minus lambda less than equal to 0, and that will be the standard form that we have seen. And of course, we can't get xij equal to 0, 1. We will have xij more than equal to 0 because we don't want negative values. So for all I in j and j in m. Do we need the constraint xij less than equal to 1? No, right? Why? Yeah, this constraint along with this non-negativity restriction says that no xij can take a value more than 1. So although this should have been relaxed to xij belongs to the 0, 1 interval, the upper bound 1 is not required because this is automatically giving us that restriction. Okay, so we have this LP, and now we should ask ourselves, is this a good LP? Now, good in what sense? So consider the following scenario. So this particular case we want to consider. Only one job with time t on all machines. What is the optimal make span here? So if we just say that, if we just stick to our original restrictions that a job can get only one machine, then we can assign this job to only one machine, the make span will be t. Okay, so optimal make span is t. What will the LP do?
It will actually distribute the job on all the machines equally.
Exactly. So this LP doesn't care whether xij's are integral or not. It will just try to minimize lambda. So what it will do is to distribute this job across all the machines. So since we don't have integrality constraint here, the xij's can take fractional values. So LP optimum will be, so it will be T over M, because it will distribute this job equally across all machines so that all these constraints will be met. Right? So this value will be 1 over m for every variable, and that will sum to 1 because we are summing over m of them. And here it will be 1 over m times t, so the next one will be t over m. So this says that this LP is not particularly good or particularly useful for us because this LP has a large integrality gap. Does everyone remember what integrality gap is? It is just the ratio of integral optimum to fractional optimum. That is t over m, which is equal to m, and for any instance m can be any large value, so this is not a bounded value at all. In other words, if the integrality gap is large, then we cannot have a small approximation using that particular LP. So suppose this is LP optimum, this is integral optimum, and say this is our solution. Now if this gap itself is m factor, how are we defining our approximation ratio? We don't know this value, so we are always comparing our solution with the LP optimum. But if this can be as large as m, then this cannot be smaller than. So if we stick to this LP, we cannot get an approximation ratio which is better than m. We have to design a different LP. Any questions so far? Don't get lost. It's perfectly fine to ask questions and seek clarifications. Your questions might help others also who are a bit reluctant to ask questions. Okay, so now we have to come up with a different LP. What is the problem with this LP? I mean, why are we getting such a large integrality gap? In an intuitive sense, the make span we are allowing it to be too small compared to the processing time of this job. Right? So what we will do is precisely we will avoid this situation, that is here the make span is smaller than this individual processing time, so we will not allow that. So here we will actually fix some lambda. And we should not allow jobs to be scheduled on a machine if they have more than lambda processing time on that machine. So remove ij pairs if Pij is more than lambda. Because if our make span is lambda, then we cannot have job I executing on machine J with Pij more than lambda. A fractional solution would allow it, but precisely that is what we don't want to allow. Yeah.
Then how did that LP suggest that lambda is smaller than make span?
So here our make span is turning out to be T over N.
Oh, okay.
Right? But on the other hand, integrally, if we want to assign this job integrally, the make span cannot be smaller than T. So in that scenario, if we fix T over M make span, it will just remove all ij pairs, that is all job machine pairs. Basically, don't allow a very small make span, because if you allow very small make span, then you are bound to get a fractional solution, which is not very useful in getting an integral solution close to it. Yeah.
Can't we add lambda greater than or equal to Pij as a constraint?
But which Pij?
For every Pij, for every Ij.
That is not required, right? Because it's too strong a constraint. Maybe one particular job machine pair has some 100 processing time, but everything else is within 10. It's not that, I mean, the processing times are not identical across machines. Otherwise, we could have done that. So you don't want to say that lambda is more than all Pijs. Anything else? Oh. Arka?
How exactly do we fix the mixed-band lambda to remove ij pairs?
Yeah, so we will do a binary search on lambda. So I will come to that once we write this LP. So just 2 minutes. So define S lambda to be the set of ij pairs such that Pij is less than or equal to lambda. So we will have variables corresponding to only these pairs, not all ij pairs like we had here. And now we will have same constraints. The new LP will become. Now this LP depends on the fixing of lambda, so I will write it as a function of lambda. This LP has same constraints again. Every job should be assigned to exactly one machine. And Okay, now I don't want to say I equal to 1 to n, I want to say I in S lambda. So, since all xij variables are not present, I don't want to sum over I equal to 1 to n. I just want to sum over those i's so that the particular ij pair belongs to our set S lambda. The remaining things we have removed, we have just decided that such jobs will not be scheduled on such machines and removed those clauses. Those variables are not there anymore.
Some jobs may not be assigned.
It's okay, you can ask again. Yeah, some jobs may not be assigned. So why? One reason could be that a job, a job doesn't appear in S lambda at all for any machine. But then that is not a feasible schedule at all, right? Or that is not a feasible lambda at all. Right? If we set lambda to be too small, we will end up removing all pairs, and that is not a nice thing. But then such a lambda is not a valid lambda for us.
So if we have such a lambda in the LP formulation, summation xij equals 1 for all I belongs to j, that won't happen for that lambda, because if some job isn't scheduled, then the sum won't be 1.
Here also I should write over only S lambda. Oops. So J such that Ij belongs to S lambda. What is the question, sorry?
Oh no, I was saying that if summation xij equals 1, if we sum over all the machines for a particular job and a lambda isn't feasible, that is, there exists a job which is not there in S lambda, then the sum won't be 1 for
Yeah.
if we sum over that
Yes.
job.
Yes, so the LP will not be feasible because this says that each job should be assigned to some machine, but here this says that the make span has to be at most lambda. So if both of these cannot be met, then the LP will be infeasible. So if you see, this LP has no objective function. All we are concerned is there a feasible solution or not? So depending on our value of lambda, the feasibility will change. Of course, larger lambda doesn't create a problem, because if we allow a larger value of make span, the same solution remains feasible. So this is the LP we will work with, and we will ask ourselves, is there a feasible solution? If you are not comfortable with that, you can define any dummy objective function. That's it. We can now get rid of this LP.
This is a good chance to ask.
Sorry?
This is a good chance to ask you questions.
Yes. Alright, so let's say we solve this LP and get one feasible solution. Well, for which lambda is a question, right? So let's define lambda star be the minimum lambda for which the LP is feasible. So we do a binary search on lambda. Minimum value is of course 0. The maximum will be a loose upper bound like sum of all processing times. The max span cannot be more than that. So do a binary search on lambda. Ask if this LP is feasible. And this way you can get the minimum lambda star for which this is feasible. Below this it is not feasible. How does this compare with the optimal max span? Okay, of course optimal max span value is feasible. So this lambda star has to be less than equal to that. It can also be smaller, right? Because this LP has the freedom to assign jobs fractionally. So if at all it can do better than the optimal solution which is necessarily integral. So this is an observation that lambda star is less than or equal to optimum max span.
How did we get the candidate values lambda?
Yeah, so here let me write it. So we will do a binary search on lambda. In this interval, that is 0 to, let's say, sum over all ij pij. So for this value, of course, it is going to be feasible. For this, it will be infeasible. So every time we set lambda to like the middle of the interval and ask, is the LP feasible? If the answer is yes, we will reduce it to again the midpoint of the smaller interval and so on.
I have a question. So one thing is not immediately clear, that suppose lambda star is the minimum lambda for which the okay, so I mean, why for a smaller I mean, intuitively, if we make lambda smaller, then like the LP should like would want to become infeasible sort of, but why is that apparent from these constraints?
Because whatever is feasible for a smaller value of lambda is also feasible for a larger value of lambda. If you have a feasible solution for a particular value of lambda and you increase the lambda value, the same solution remains feasible.
Is that entirely true? Because if I increase lambda, my set could grow larger and my left hand side could be summing over more elements.
Sure, but the new things that appear here, you can just set them to 0 and all these constraints will be met.
Oh,
Every job is
Right.
getting assigned.
right.
So even if new variables appear, you can just set them to 0 and that will give a feasible solution for the constraints.
Thank you.
Sorry, I didn't get the assigning of the new variables to 0 part.
So what is the concern? The concern is that if we change value of lambda, our set S lambda changes. In particular, if we increase lambda, S lambda also increases. More variables will appear because more jobs will satisfy this. So since we have a feasible solution for a smaller value of lambda, in particular we have every job being assigned to some machine. So we can set the extra variable which appear because of increase in lambda to 0. So we don't have to do anything for those. Okay, so of course optimal max span value is feasible because there is such an assignment. Since our LP has the freedom to assign jobs fractionally, it can possibly do better than the integral optimal max span. So lambda star will be less than equal to optimal max span. Now let x be and I have to be specific about lambda. So x be a solution to LP lambda star. X can have fractional values as well. If at all x turns out to be integral, that is great. We have an integral solution with max span lambda star. Since this is the minimum value, even with fractional values allowed, we will have optimal solution itself. So that is too much to hope for. So what happens if x has lots of integral values but very few fractional values? So let's depict this in terms of a bipartite graph. Here there are jobs and here there are machines. And let's denote non-zero xij values by ages. So ages correspond to xij being non-zero. So I am drawing this kind of a graph. Can you see which jobs are integrally assigned and which ones are fractionally assigned here?
Degree 1.
Yes. So, for example, jobs 2, 4 and 5, they have only 1 degree, and this constraint says that that particular xij should be 1. So, we have put edges only corresponding to the non-zero ones and the zeros we have ignored. So, in particular, these jobs are integrally assigned in this solution that I have drawn.
So, multiple jobs can be assigned to one machine?
Yes, because we have assume that we have many more jobs compared to the number of machines. So a machine can get many jobs, but a job doesn't go to many machines.
Can no jobs be assigned to a machine?
If that is the case, then sure, yes. In particular, if the machine is very slow and the processing times are too large, we might want to discard that machine and use the rest.
Ma'am, if they are assigning jobs fractionally, like can a job be running parallel to 2 machines at the same time?
Yeah, so here we are only giving an assignment, right? As in we are not saying how they are scheduled or what their sequencing is on a particular machine. So since this assignment is not our ultimate target, we will allow parallel processing and everything.
So half of a job can be running on machine 1 and half of the same job can be running on machine 2 at the same time.
Yes, so that is what the LP solution tells. Not just half, it could be half on one machine, 1/3 on another, and 1/6 on another. So it could be like this as well. So this job gets assigned to 3 machines. Of course, fractionally maybe something like half, 1/3, and what remains 1/6. That is something of this sort.
Can in the first LP, like before this binary search, can we have lambda greater than or equal to min of Pij, like for every job? And
Yeah, but that wouldn't turn out to be sufficient. I mean, one can add another job with only 1 processing time, and then that will set on the lambda to be more than equal to 1. But that's not good enough still. Okay, so
Are we allowed to take things like minimum? Not in the objective.
minimum?
In the constraint, are we allowed to use things like minimum?
No, we are not using.
Here we are not used. but
Hmm.
it's allowed.
That wouldn't keep it linear. So we have to get rid of minimum or mod or such things.
So that can be translated to an inequality, right? Let's say. I mean, it should be greater than or equal to.
No, minimum over processing times is not a problem, right? Processing times are not variables; they are part of our input.
One more thing. So, with reference to a previous question, if for one lambda 1, this LP lambda is feasible, lambda 1 is feasible, and then we know that for all lambda greater than lambda 1 it will be feasible because
Yes.
we can set the extra variables to 0.
Yes.
But there is just one thing that is there, that suppose if lambda increases, a new job comes into the picture which was not in S lambda before. So
we will not call such a LP feasible at all if some job doesn't get any machine.
So that has to be included in the constraint somehow. Because if a new job is included, then that summation xij has to equal 1 for that job.
If at all this set is empty for a particular I, then that empty set cannot give us a sum of 1.
Okay.
So we will at
That-
an intuitive level we will assume that.
Okay, that is actually included by the first equation. Because,
In some sense, yes.
yeah, because for the empty set it won't sum to 1. Okay, thank you.
Okay, so where are we? So there are some jobs which get fractionally assigned like this, some jobs which get integrally assigned. That is very good. Now suppose we keep the fractional jobs aside and look at only the integral jobs. So suppose we decide that fractional jobs will be discarded for a moment and focus on integral jobs. What can we say about their make span? So their make span is still only lambda star, which is in fact less than or equal to the optimal make span. So the integral jobs can be assigned to whichever machine the LP assigns them to. So these assignments we can freeze and they give us a make span of at most lambda star. The question is only about the fractional jobs and we will come to them in a moment. Okay, so what are we doing? We have a fractional solution. We somehow want to get an integral solution which is not too bad compared to lambda star, because if we get it to be some 2 times lambda star or constant times lambda star, it will also be that much constant times optimal. That will be good for us because it will give a constant approximation. Yes? Sorry?
What is the integrality gap of this LP?
So we will show a two-approximation using it, but we will not analyze its integrality gap. Right? So you can think about constructing an example where it is exactly 2. It will probably turn out to be 2 times 1 minus epsilon or some such, but we will not analyze it today. We will focus on how to get an integral solution from this fractional one. It will turn out to be a 2 approximation, so integrality gap has to be smaller than 2 or less. Now if at, okay, so one observation that we make here is that assignment of integral jobs as per X gives make span less than equal to lambda star. Now what if now let's focus on the fractional jobs and see what to do with them. Now suppose we have only few fractional jobs and there is a nice property that every machine can get at most one fractional job, in the sense that now this job is fractional. It is assigned to 3 machines. We have to assign it to exactly one of the 3 machines. That is what the rounding is. One of these fractions we want to change to 1. Remaining fractions we want to be 0. So suppose we can get an assignment where every machine gets at most one such fractional job rounded to it.
Do we assign to the highest fraction one?
No, we will not do that right now. But let's say we have this property that every machine gets at most one fractional job rounded to it. How much will it increase our make span? Let me call this property star. It says that there is a way to round fractional jobs. Such that each machine gets at most one such job. How much will it increase our make span? Say it again.
Lambda star at max.
Yes. So currently with integral assignment our make span is lambda star. So if we look at our graph of jobs versus machines, again these are the integrally assigned jobs and so on and so forth. So this make span is only lambda star. This consists of only integral jobs. So all these jobs are integral. Now we are hoping for this property that every machine will get at most one fractional job rounded to it. So this machine gets 1, maybe this machine gets 1, and maybe this machine gets nothing. So now this rounding is happening only along those pairs which are present in S lambda. which means the extra processing time that each machine is getting or extra work that each machine is getting is no more than lambda star. So this additional make span is not going to be more than lambda star. Am I making sense here? So we had a lambda star make span with fractional and integral assignment mix. Keep aside the fractional assignments, the integral assignments is still a valid assignment for those jobs. Their make span is at most lambda star because we have only removed some things from this solution, the LP solution. Now, for the fractional jobs, if this property holds that we can assign only one job to each machine, and that we do only from the pairs S lambda of course, then each machine gets extra work of at most lambda star. So our processing time doesn't increase by more than lambda star. So what is our total make span? The original lambda star with integral assignments plus this extra at most lambda star from the rounding of the fractional ones. So this total is at most 2 times lambda star. So the claim is that if we have this property star, it implies 2 times lambda star make span, which is less than equal to 2 times in optimal make span. See if you get this correctly, then we will focus on how to get these properties. Yes. Okay, so I have not told how we will assign fractional jobs, but suppose the graph between fractional jobs and integral jobs is such that we can assign, the graph between fractional jobs and machines is such that we can assign at most one fractional job to each machine. So for example, this job has 3 machines currently assigned to it by the LP solution. We want to assign only one. So instead of getting half of this job, this machine is getting 1 fraction of this job. So the processing time assigned to this machine or the work of this machine is getting increased. Right? So if at all we say that every machine gets at most one such job assigned to it among the fractional jobs, then how much can the work of every machine increase? It gets at most one extra job from the fractional set. Hence, it gets at most lambda star of extra work.
That is possible only if we get a matching of the fractional values, right? Like
Yes. So essentially what we want is the graph between fractional jobs and machines has a matching. And that matching should assign every job.
So we can improve this bound if we can like improve this fractional thing. We know how many of them are there. Then instead of lambda star, it will be like.
It cannot be smaller than lambda star in a guaranteed manner, right? Because even one job can raise the processing time by lambda star value. But at least we are currently having the promise of 2 times lambda star. So each machine gets lambda star from the integral assignment, at most one extra job from the fractional assignment, and hence at most one another lambda star factor of work because of fractional assignment. So the two together make 2 lambda star processing time, which is a 2 approximation. So what we have currently is, if we can ensure this property, or if we can ensure that there is a matching between fractional jobs and machines, where each job gets assigned and each machine gets exactly 1 job, so then we can expect, or we can get a 2 approximation. So property star implies a two approximation.
So this property star we are talking about, this is over the set S lambda star basically. So the edges that are present in S lambda star, that is that graph,
Yes, yes.
by Vertex graph.
Yes.
Same. So over that, so all
Because
of
the
the
edges correspond to xi edges being non-zero. But what are xi edges? They come only from the set S lambda star.
right. So
So the
since
edges-
all of them have time lesser than or equal to lambda star, so it's the
Yes. So the corresponding processing time that a machine gets is
that
lambda
gets
star.
added since it's lesser than or equal to one job, so it's lesser than or equal to lambda star.
Yes.
Okay, thank you.
Now, in our LP solution, what if the number of fractionally assigned jobs remaining is more than the number of machines?
Exactly. So that
Then our mixed-span can increase by more than lambda star, right? When we round.
yeah, sure. That is a very good concern. That's a very good point. That why will we have this property star in the first place, or why will we have at most m many fractional jobs in the first place? So as it turns out, the concern is correct in the sense that we cannot use any LP solution. What we have to use is a vertex solution to the LP.
On what basis do we assign that fractional part to the integral jobs?
I have not told you how we will assign, but if at all we look at the graph between the fractional jobs and machines, and we have a matching there which assigns every job, then we will have this property star. Essentially, we only have to find a matching between jobs and machines, and the matching should match all the jobs.
So this property star is in the case of like assigning one job per machine.
Yes, among the fractional ones. The integral ones get absorbed within this lambda star factor because the LP tells us how to assign them. The fractional ones we are assigning in an
I have another question. So instead of solving this problem using LP, can we just order the jobs in their descending order of the time taken and then
But on which
assign-
machine is a question, right? So this is a good point in the sense that if we didn't have different processing times on each machine, then you wouldn't need LP. You would get a two approximation without using LPs. And this you will solve in the problem set today. So, so if the machines are identical, every job takes the same amount of time on each machine. The problem becomes simpler. You don't need LP. You get a two approximation very easily. And in fact, even better than that. So, yes, do tell me whether that will turn out to be a nice solution. You will enjoy solving it. Okay, so our concern now is how to get our nice property star. So, as I said, a typical LP solution can give us several fractional jobs, or maybe all jobs get fractionally assigned. So, we don't want arbitrary LP solutions. We will have a we will have a vertex solution to the LP. So, a vertex solution to LP lambda star satisfies property star. This is what we want to prove. What is a vertex solution?
Corner point.
Yes. So if you look at the feasible region of the LP, maybe I should change. Yeah, so if you look at the feasible region of the LP, then the corner points of the feasible region are the vertex solutions. Now what is the nice thing about them? So for example, this is a constraint and this is a constraint zone, and this vertex is formed by the intersection of the corresponding constraints. So what is the property of this vertex? That when we look at this particular solution, this constraint should be satisfied with equality because this point lies on this line. Similarly, this constraint should be satisfied with equality. So this is in 2 dimensions, that a vertex or a corner is defined by intersection of 2 constraints. In general, if you look at some r dimensions, you will need r many constraints to be tight or to have equality at a particular vertex. So I hope everybody is comfortable, but typically I give the intuition of the room that we are in, which acts as a nice polytope to give a good enough intuition. So to define the corner of this room, we want the intersection of this wall, and the roof, and similarly for other corners. So in general, to get a vertex solution in r dimensions, we need r type constraints. When I say tight constraint, that means although we have less than equal to here and here, or here greater than equal to, we need equality. Is everybody comfortable with this? Otherwise I will explain more. Yeah.
I just wanted to ask that since we are running binary search on the values of lambda, doesn't it intuitively make sense that the point at which we finally end lambda star, well, that should just be a single point instead of a
That's a single value, right?
Yeah. So when we finally end up at lambda star, the size of the feasible region, shouldn't that it end up just being a single point?
Not necessarily. For example, even for the case that we considered, there could be several solutions, right? So the single job and m machines case we considered, the job can actually go to any machine. So there are m possible solutions there, all with same make span. So even if you catch hold of this particular lambda star, you can have several ways of assigning jobs to machines and getting lambda star. So let's define size of S lambda star to be R. So there are R many variables. So our LP has, or the feasible region actually lives in R dimensions, or our feasible region is a R dimensional polytope. And to define its vertex, we need R many type constraints, or R constraints have to intersect to define a vertex. So just like 2 lines define a point in 2 dimensions, 3 planes define intersection of 3 planes gives a point in 3 dimensions, and so on. Here we will need R many. Now how do we get R many type constraints? How many constraints are there of this kind? So there are 3 kinds of constraints, right? These ones which are anyway equalities. So by type constraints I mean equalities. So how do we get R many type constraints? So there are these which are anyway equalities. There are n many of them. Even if all these constraints are satisfied with equality, how many will they be? Only m. So m plus n constraints can come from here among the R equalities that we need. The remaining R minus m minus n have to come from here.
this binary search on lambda, it won't run in like polynomial time, right? Like,
It will be log of total processing times.
and that value might be very large.
Sure, but this is part of our input, right? The PIJs are part of inputs, they are represented in binary.
Okay.
So log of them is
Okay.
Okay. So what I want to claim is the following. We are looking at a vertex solution of the LP. We know that R many constraints have to be typed. There are only m plus n many of the first and second kind. So remaining R minus m minus n have to come from here. So at most m plus n variables can be non-zero in a vertex solution. Is this claim clear from what I said? Again, our LP is in R dimensions because we have R variables. M plus n tight constraints can come from here to define a vertex solution. The R minus m minus n have to be equalities from this part. So R minus m minus n many variables have to take 0 value because this has to be equal. So out of R variables, R minus m minus n must be 0 because we need R equalities, and to get R equalities at least R minus m minus n have to be from this part.
Can R be equal to m plus n also?
Then we will have a very sparse graph and we can deal it. In any case, then all of them can be non-zero, but that is still n plus n. So we are really concerned if there are lots of variables, then what if all of them, many of them turn out to be non-zero? This says that at a vertex solution that cannot be the case. So we will have at most m plus n non-zero variables. How many of them can be fractionally assigned? We don't want too many fractional values because we are hoping for a matching between fractional jobs and machines. So how many of them can have fractional values? So let's define like this. Let I be set of jobs such that xij equals 1 and if be set of jobs, well, there exists j such that xij equals 2. J, so if be the set of jobs which are fractionally assigned, that is there exists j such that xij belongs to 0 1. Okay, so in particular I are integral jobs or integrally assigned jobs and F are fractionally assigned jobs. This is a slightly, I mean, I'm not using the right words, I should say fractionally assigned jobs, but this is what I write for. The jobs have to be executed in full because of this constraint, but because they are fractional, they will be, the one part will come from various different machines. What is the size of I plus F? N, right? Because every job has to be either integrally assigned or fractionally assigned. What can we say about
Less than equal to
less than equal to
m.
n? Okay,
M.
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 That is right. So let me come to that. So again, this bipartite graph that we were looking at will turn out to be useful. So some jobs are integrally assigned and some are fractionally assigned by the LP. So again, this is J side, this is N side. And the edges only focus on non-zero excisions. Now, since a fractional job gets fractionally assigned, it has to get assigned to at least 2 machines. So when we say xij belongs to 0 1, for every job there have to be at least 2 such excises. But then for every job in F, at least 2 excises have to be non-zero. But what is the total number of non-zero variables? It is only m plus n. So number of non-zero variables is, of course, these are completely assigned, so those variables are non-zero, 1 per job. And there have to be 2 per fractional job. Maybe 3 or 4 or even 10, but at least 2. So because of claim 1 and this, we have is I plus 2 times mod f is less than or equal to m plus n. Now compare these two equations. This tells us that f is at most m. So everybody with me? So there are different components, and even if you have lost in a particular component of the proof, you can still come back. So believe claim 1 for now and say that, also believe that we have the right value of lambda star, and you will follow the rest.
Could you please repeat that 2 times f?
So it is clear that these jobs are actually fractionally assigned. So they have to be assigned to at least 2 machines, possibly more. So how many non-zero variables does this set contribute? At least 2 per job. So we have 2 times mod f here. But these many variables have to be non-zero. These many have to be non-zero. The total non-zero variables is this. So we have this second inequality. So from the first and second inequality, we can deduce that number of fractionally assigned jobs is at most m.
We have not proved claim 1 as of yet.
Say it again.
We are still to prove claim 1.
Well, I did not write the proof, but I said that claim 1 has to be true because we can get only m plus n many equalities from here. R equalities is what we need to define a vertex. M plus n come from here. R minus m minus n have to be from this part. But then if R minus m minus n variables must be 0, then how many are non-zero? At most m plus n, because there are total R many variables. So I have not written the proof, but I just described it. Anything else? Now we are very close to getting a matching between machines and fractional jobs, right?
I mean, but still one.
Exactly. So this alone doesn't guarantee us a matching. Yeah. So let's do a little more work and see that there is a matching. That is, our property star is indeed met. So now, as I said earlier also, that the integral jobs we will freeze according to what the LP suggests to us, and that will give us at most a lambda star processing time. So now only focus on fractional jobs and look at the graph between fractional jobs and machines. Okay, so forget about the integrally assigned jobs. The machines have to be there, we can't remove them. Actually, this machine also can go away. Let's assume that it has some job assigned. Now, how many vertices does this graph have?
At most 2.
Yeah, m on one side and m on the other side. But then at most m plus n variables are non-zero, so the number of edges can be at most m plus n. Okay, so what we want to claim is that this graph is what is called as a pseudo forest. So let me tell you what it is. So let me define pseudo tree. So basically we want to look at this graph, show that it has certain special properties, and we can always extract a matching between jobs and machines where every job gets assigned. Okay, so I will define this pseudo tree for that. It's not very difficult. It is a graph with at most one cycle. How does the graph look like? You can convince that it can be nothing but tree plus one edge if the graph is connected. So for a connected graph, this is tree plus one edge. So very close to a tree, but one extra edge. What is the advantage of having a pseudo tree? So let's see why this pseudo tree is helpful, or why it will be helpful for us to show that this graph is a pseudo tree. Can we extract a matching if this property is satisfied? Okay, how?
Because if it has only one cycle, then and we know that a bipartite graph does not have outline cycles, so we can move from one vertex on the machine side to one vertex on the job side and so on and so forth. So we directly have an assignment of the first machine on the cycle to the first job on the cycle, then the second machine on the cycle to the second job on the cycle, and so on and so forth.
Yeah, so exactly. So that is what we will do. Say it again. Yes, so let's do the other way around. So suppose this is our graph, and assume that it is a pseudo tree, that is it is tree plus just one edge. So we can still define leaves, right? Although it's not quite a tree. Pretend that it's a tree. Define the leaves as degree 1 vertices as usual. Which vertices can have degree 1?
Machines.
Only machines, right? Because jobs have degree at least 2 since they are fractionally assigned. So there are some leaves which are all machines. Now for these machines, the one job that they can get is only this one. So assign the leaves the only job they are connected to. I mean, here we are done with this, the graph becomes empty. But suppose there was something more, right? Some cycle of this sort. Okay, so something like this. So again, go to the leaves, assign the only job which they have, remove the machine as well as job, because we don't want to assign more than one job to any machine, and this machine gets this job, this machine gets this job. Forget about those machines and those jobs. Now either we will have, can this create more leaves by the way? If we remove a leaf and its parent, can we get more leaves?
Yeah,
Yeah, we can.
formulation will come.
Okay, how?
Because if we remove the node, if we remove the job J, then its corresponding edge to another machine, it can get removed.
Yes.
And that could become a list.
Yes, so for example, this machine will lose this edge, it will have only this edge, so it can become a new leaf. Can a job become a leaf? No, right? Because this machine has only one edge, and that particular edge is getting removed along with the job machine pair itself. So no job can become a leaf. So our invariant that leaves can only be machines still holds.
But I still don't get why it is a pseudo tree.
No, we have not proved it. We are just first we should see why it is useful to have a pseudo tree. Because if we do all the work of proving it to be a pseudo tree and then find that it's not useful, that's not good. So let's see why it is important to show that.
I have one question. Why should there be leaves at all?
Otherwise, what is what good? Yeah, that's a good question. So why? Otherwise, what will the structure? A collection of cycles, right? Sure, that's a good point. So if there is a leaf, assign and remove that job as well as that machine. No new job can become a leaf. Machines can become new machines can become leaves. We can continue our procedure. At some point, we will be stuck because we will have no leaves. In particular, we can also be stuck at the beginning itself if we don't have leaves. The picture could be like this. What do we do in this case? Now this, if there is no leaf, we can only have a collection of vertex disjoint cycles because of this property. So let me write all this down. So this is G. I will not write J here, I will write F here so that you will remember that we are focusing on fractional jobs. So let G be a pseudo tree. We will show that it is a pseudo tree in a moment. But currently assume this and complete our algorithm. So suppose G is a pseudo tree. While there exists a leaf, and our observation is that only machines can be leaves. So while there exists a leaf J, assign the job I such that Ij belongs to G. Assign the job I to J. Remove Ij. So we will keep doing this while there is a leaf. We said that no job can ever become a leaf by this procedure. Now there is no leaf. So what happens? Either G is empty. Empty meaning no edges. We don't care if there are some unassigned machines. Either G is empty or it is a collection of vertex disjoint cycles.
Then we will get a matching.
Exactly. And of course no odd cycle because it's a bipartite graph, so vertex disjoint even cycles. But in an even cycle one can always get a matching. Just take alternate edges and you will get a matching. Like this. Find a matching in each cycle by taking alternate edges. So, is everybody convinced that if we have our graph as a pseudo tree, we can assign at most one fractional job to each machine and be done with a rounding procedure and two approximation. Any question? Anything? Any confusion? Any other concern? Yeah.
So a pseudo tree with the following constraints that it's a bipartite graph and only the leaves are on one side.
Yes.
These are the additional constraints.
Yes.
Okay.
How many? What is the relation between number of vertices and number of edges for a pseudo tree? They will be equal, right? Because in a tree the number of edges is number of vertices minus 1. Here there is one extra edge. So there will be equal number of vertices and edges. Okay, so what all did we do? We wrote this particular LP. We said that we will do a binary search on lambda and get the minimum lambda star so that the LP becomes feasible. Once that happens, we will only take a vertex solution because that vertex solution will have some desired properties. In particular, the vertex solution will have at most m many fractionally assigned jobs. The integrally assigned jobs we can freeze. They don't take time more than lambda star because it is still a valid solution to the LP. And for the fractionally assigned jobs, there can be at most m of them. We said that if the graph between the fractionally assigned jobs and machines is a pseudo tree, then we can ensure that every machine gets at most one of these jobs. And Hence every machine gets at most lambda star amount of extra work apart from the integral jobs that it has got. So lambda star work for every machine comes from work meaning time. So lambda star time for every machine comes from integral jobs. At most extra lambda star comes from here. So we get at most 2 times lambda star makes time, and that is at most 2 times optimal makes time. So we have a 2 approximation modulo the fact that we prove that this graph is a pseudo tree. Yeah. 1 second.
Why you didn't get 2 leaves such that they point to the same machine? Okay, machine learning, fine.
Doesn't matter. Even if it is like this, you can just assign any one machine this job. It's still one per machine. Remove this job, this machine, and then this machine will have no edge. It will not get any fractional job. It has no complaints about. Okay, so apart from proving that G is a pseudo tree, we are done with our 2 approximations. Let's focus on this and I will erase the rest. Yeah, before I erase, let's see what is the number of vertices and edges here. So number of vertices is 2m. What is the number of edges? So there are at most m plus n non-zero variables. Minus I has to be subtracted. Yeah, so let's do that once. Because we said that for a pseudo tree, the number of vertices and edges should be equal. At least that should hold here. So, number of vertices is mod f plus m, which is less than or equal to 2m. Number of edges is n plus n minus mod I. Now since mod f is less than n, we have mod I to be more than or equal to n minus n. Does everybody get the calculation? So mod f is less than or equal to m, but mod I plus mod f is exactly n. So mod I has to be more than or equal to n minus n. So since we are removing integral jobs after assigning them, these many edges are getting lost. So these many edges will be lost. Total number of edges can be only this much because these are the non-zero ones, non-zero variables. So m plus n minus mod I, and because of this inequality, we have number of edges to be at most 2m. So there are 2m vertices, at most 2m many edges. So at least one property for this, one requirement for pseudo tree is satisfied. Now if G is connected, then this is sufficient to say that this is a pseudo tree, because it has exactly one more edge than what would make it a tree, and since it is connected, it should have exactly one cycle.
Could you repeat the last one?
Okay, so let me write this as a formal claim. If G is connected, then it is a pseudo tree. What we know is that G has 2m many vertices and at most 2m many edges.
Both are inequalities, right?
But if it is connected, then it holds with equality, because the number of edges in a pseudo tree, in a connected graph, the number of vertices should be, number of edges should be equal to, greater than or equal to number of.
Yeah, connectivity alone says that the number of edges cannot be too few, right? So if G is connected, then number of edges is at least the number of vertices minus 1. So it is either a tree or a pseudo tree. That can be too much, too large.
Number of vertices is at most 2, not 2.
Yes.
But then how
So so let's do this account a little. So basically, when we say mod I here, that mod I is also n minus mod f, right? So I think we should do this accounting a little better. So number of vertices is mod f plus m. Let me do this a little better. Okay, so yeah, so number of vertices is mod f plus m. Number of edges is m plus n minus mod I, which is m plus n. Now I itself is n minus mod f. Am I doing it right? So this n will get cancelled and it will be m plus mod f. So number of vertices is also m plus mod f, number of edges is also m plus mod f. Yeah, so number of vertices is exactly m plus mod f, number of edges is at most m plus mod f. No.
Right.
Alright, so if it is connected, it is a pseudo tree because it has at most as many edges as the number of vertices. And then it cannot be anything but tree plus one edge because connectivity ensures that it is at least a tree and there is only one extra edge. Now, if it is not connected, we have to do a little more work, which I will not get into too many details, but let me give some intuition as to what we do if G is not connected.
You have 10 more minutes, right? We started a bit late. So.
Sure. Thanks.
So not connected means the case where there exists machines for which there are no fractional jobs assigned.
That is a good case because then we can focus on the only the connected component.
Oh, okay.
The case we will be concerned with is when there are multiple connected components.
Right.
I will not write it as a claim. So it will look like this. So there are some vertices and edges here. I am not counting the number of vertices versus number of edges, but assume that it is one component. This sort. So suppose G has multiple components. We want to say that each component must be a pseudo tree. Now, how would we claim that? Sorry?
Each component is either a tree or a pseudo tree or
So pseudo tree also encompasses trees, right? Because it is at most one. So every tree also qualifies for being a pseudo tree. So here we need to do a little more work in the sense that we look at each component separately. So just focus on these jobs and these machines and pretend that only this was your input. So you wrote the LP on, and found the lambda star only for this input, and so on and so forth. So again, what I claim is that if you restrict your LP and the solution X to this input, this is a valid solution to the restricted LP, and it is also a vertex solution if the original solution was a vertex solution. So let me write this down. So let C be a connected component. So focus on the sub instance C, that is only the jobs and machines which appear in C. The LP restricted to C is a feasible LP. That is of course true because it's part of the original solution. And X restricted to C is a vertex solution. I will clarify this part, so don't get lost here or don't think that I am doing something very difficult. All we are trying to say is that if this G is disconnected, it has multiple connected components, then we will look at only this as our input and say that the original LP with constraints restricted to only these jobs and these machines and so on is still a feasible LP with the same value lambda star. Since we are removing some jobs and some machine, in particular these jobs and these machines, everything else should remain as it is. So this LP defined on the small part is also a feasible LP. Our original solution is X, but that part of X, or only those variables from X which correspond to these job machine pairs, they also form a vertex solution to this restriction of the LP. Why? Because if that is not a vertex solution, then the overall solution will not be a vertex solution. So the one property of vertex solution which I did not mention, maybe it's worth mentioning right now, since we have 5 minutes, is the following. That is, a vertex solution, or it is a corner point of the feasible region, cannot be expressed as a convex combination of two feasible solutions. What is a convex combination? So, convex combination of A and B is some alpha times A plus 1 minus alpha times B, where alpha comes from 0, 1 and 2. So, in particular, what this says is that the vertex solution cannot be present on a line segment that joins two feasible solutions. But of course, a corner cannot be present on a line which joins two feasible solutions. Otherwise it will be a corner. So anything that lies on the line segment, something in between, cannot be called a corner. That is the intuition here. So our X solution was a vertex solution. If this was not a vertex solution, the restriction of X to this small instance, then this is a convex combination of two others. We can extend that to a convex combination for the original X as well. am trying to say here is that if we look at any C which is a connected component, it satisfies all the properties of our original vertex solution, and hence it also will have this property that its number of vertices and number of edges will satisfy this restriction, that is number of edges is at most the number of vertices. So C is a pseudo tree, because for connected graphs we already said that it's a pseudo tree. So this C is a pseudo tree. So similarly, every component is a pseudo tree. We can execute our rounding procedure on each component separately.
Why is this property
Which one? This property?
solution?
Yeah, so I'm not sure I can prove it right now, in the sense that we have enough time to prove this right now. But as I said intuitively, that being a convex combination means it lies on the line segment which joins two feasible solutions. But then we cannot call it a corner. So yeah, one needs to prove it formally, but I will not do it right now. Intuitively, you can say that it's not on the line segment that joins the feasible parts.
Madam, can you explain proof of claim to answer?
So G is connected. Its number of edges is at most the number of vertices. If it is at most the number of vertices minus 1, it's a tree itself. Now it has one extra edge. How else can it look like? Can I have only one cycle? So it is a pseudo tree.
So one question, that all we wanted to show that if we restrict the graph on F and M, then there is a F saturated matching, right?
Yes.
So why don't we use Hall's theorem
You can actually, I think you can show it using Hall's theorem.
and show some contradiction of the feasibility if no match?
I think it should be possible to show it using Hall's theorem. Just that I have not worked out the details of that too, but they are worth working on. And that might turn out to be more elementary than this.
One more questions, then we'll take questions. No questions. Then let's thank Rajata. We have a gift from.
Oh, thank you so much. Thanks for being present and being. Thanks for inviting us.
You'll be around till.
I will be around until today evening and in fact tomorrow morning.
Okay.
If you have any questions, feel free to ask. If you found any difficulties with the homework problems, of course I am sure the TAs must have explained to you. But still, if you want to catch me,
So we'll have a shorter break and we'll still be back by 11:30. Okay.
session will be given by Ms. Krishna Hussain. So I'll introduce her again. So she is a PhD student here at IISc. She did a master's from JNU. Research interest areas lies in algorithms, computational geometry, and discrete geometry. Also, like, if you have any questions, so please raise your hand so I can pass the mic to you.
Thanks, Parag. So today we will see this hitting set problem in the geometric setting. After the duster. So let's start with some basic definitions. So one is that a set system, you might have already seen it in the earlier lectures. We have a set of points or elements, also called as the ground set, and then we have another set of subsets of X. Okay. And together this form a set system. So in computational geometry, in the geometric setting, usually we refer to this as a range space. In set system, I'll be usually referring to it as a range space. And we'll be assuming that these elements are points in the Euclidean space, and this R is a set of ranges. So every subset I'm calling as a range. Okay. Now the hitting set problem is that I want to find a subset of this set X, a finite subset, which intersects every range in R. H, a subset of X, is a hitting set, in short HS, of the range space XR if H intersects every range in the range space. This hitting set problem is that we want to find a hitting set of the smallest size. So that's the goal. Goal is to find a hitting set of smallest size. So I have to take a small example here. Say I have disks. And a bunch of points. The goal is to select a set of points which intersects every range in the range space. Right? So for instance, if I pick, so there are 5 ranges, I can pick 5 points, but I want a subset of smallest size which will hit every range. Right? So for instance, I can pick one from here, and these 3 objects are being hit, and then the remaining 2 I can hit using this point. So is the problem definition clear? Okay. Now this problem is known to be NP hard, and one can do a reduction from this vertex cover problem. So hitting set is NP hard, and you can try it on your own. It's a simple reduction from the vertex cover problem, which is already known to be an NP hard problem. Okay. Now let's consider a very special case of the range space. Suppose I give you a range space where every element is there in exactly two ranges. Or let's say even a simpler setting where every range consists of exactly two elements. You have a range space, a finite set of points and a set of ranges, and every range is having just 2 points. What do you think? Is it still NP hard, or we can come up with a volatile solution for this, for a hitting set of such instances? Got the question? I have a range space, and every range contains exactly 2 points. The question is it still NP hard? So can you see that this problem is now equivalent to the vertex cover problem, right? So still, even this humble setting where every range contains only 2 points, exactly 2 points, it still is a NP hard problem, and in fact it is equivalent to the vertex cover. So in general, the hitting set is a generalization of vertex cover, right? And you can flip the setup. You can say that, okay, what if every element is contained in exactly 2 ranges? Again, you can show that it is equivalent to vertex cover, right? So let's see, the problem is NP hard, but what if we restrict our ranges to one dimension? So say we are in 1D, and now I have the set of points is the entire real line, and the ranges are, okay, not the entire real line, we have points on the real line, say. So x is some set of points, each xi is a real number, and range is some set of intervals. Can you solve this problem in the fitting set for 1D case optimally?
This is job scheduling.
Is it? So how do you do that? Like exactly?
Finishing time based on finishing time.
Okay. What is the, so that's the greedy approach, right, in the job. So how do you do here, like what is the algorithm here? Here you have points as well as intervals. So overlapping. So
based upon the greedy approach, we can do the overlapping intervals kind of scheduling.
Okay, so greedy is there, but what is the greedy strategy?
So basically, if a point belongs to two intervals, we can have that point in our set, and if not, we can try to have that.
So essentially, I think you are suggesting that if we pick a point which hits a large number of intervals and then recurs.
Yep.
Okay. But then, will it give an optimal solution? And meanwhile, I say it won't give us an optimal solution. You can think of another greedy strategy which will solve this problem optimally. Won't take much time. So I'll give a counter example to what was proposed. Let's say we have 3 points, and how do I? Okay, so here we have an instance, right? If you see, every point here is hitting exactly 3 intervals, right? And greedy, suppose, picks up this one. Then we will be forced, the algorithm will be forced to pick A and C as well. Whereas the optimal answer is just A and C. Okay, so this greedy approach won't work, where we pick a point which is hitting maximum number of intervals. It won't give us a optimal solution. So can you think of another greedy strategy which will work, at least for intervals?
Maybe we can pick the point which is covering the most number of remaining intervals.
So we are looking at the hitting version, not the dual covering version here.
Okay, so like once we have covered a subset, we can just remove it and then...
That is what was proposed, right? Once we have hit a certain number of intervals, you remove them and then recurse. But I give you an instance where this does not give an optimal solution.
Sort X, sort R based on finishing time.
Exactly.
Go and for
And then
engagement, put the last point in that.
Last point, yes, that is the key observation. So you sort these points on the line, you sort these intervals based on their right endpoint. Pick the interval which has the leftmost right endpoint, and for that you want to hit it and hit it with the point which is rightmost in that interval, and repeat. And you ensure that this indeed gives you an optimal solution. Right? But the moment you move to 2-dimension, problem is already known to be NP-hard. Right? So here is this reduction from vertex cover. It works for the general set system. Then later, I think in early 80s, it was proven that even in 2D, if we have, say, unit squares, the ranges are unit squares. For this also, so hitting set for unit squares was shown to be NP-hard. Okay, and unit squares, then rectangles, discs, half spaces, it's an NP-hard problem. So we'll be looking at approximation algorithms for the hitting set. In 2D we'll see how to get an approximation algorithm. So before we start, can you suggest one simple algorithm that will work in 2D? Hitting set, you have geometric ranges, say, like some variant of greedy again covering. Yeah, so the one that was proposed, right? You pick the one which hits largest number of ranges and then recurs. Remove that and recurs. So one can show that it will give you log and approximation. Right? You must have seen that standard example in the set cover thing, and you can mimic that to show an instance for the hitting set. Right? So greedy, where the where you are picking point that hits maximum number of ranges, this will give you a log n approximation. Okay.
So, sorry ma'am, I didn't understand the sorting solution.
Sort for the intervals case?
Yeah.
Okay. So we have these intervals sorted by the right endpoints. So in that case, this is the first interval I'll consider, then second, let's say it's ending here, 3, 4 and 5. Now you process these intervals in this order. You take the first interval, we want to hit it, pick the point which is to the right, which is hitting this and is the rightmost one. So you pick A. And then once you have this, you remove all these intervals which are already being hit by A and recurs.
How can you prove that is always optimal?
Yeah, so you can look at so such algorithms are there for other problems as well, and the approach is similar, so I don't want to do it. Okay. So any other questions so far? So in the rest of the class, we will be looking at designing this approximation algorithm better than log n approximation for the hitting set problem, and using concepts called as epsilon nets and VC dimension. Right? So let me start with the definition of what an epsilon net is, and we'll immediately see the connection with the hitting set problem. So I have a range space. Okay. And a set, let's call it n, a subset of x, is an epsilon net. So that epsilon is a real parameter between 0 and 1. It's an epsilon net for the range space if it hits every range which is epsilon heavy. Right? If there is a range, so suppose epsilon is half. So what I'm trying to say is, look at all the ranges which contains at least half of the points. So you want to pick a subset of x which will hit every range that contains at least half of the points. Right? So in general, for any epsilon, I am going to define it like for every range in the set of ranges, if the number of points in R intersection x is at least epsilon times the number of points in x, we want that this range is intersected by n. So I'm assuming that x has a finite size. If it is not, then you fix a finite subset and then define, but the definition just becomes cumbersome. Is the definition clear? So suppose you have an instance, you are given some epsilon, right? And you have an instance where you know that every range is epsilon heavy. What does that mean? And suppose there is an algorithm which can construct an epsilon net. Then that epsilon net will be a hitting set for the instance. If every range is epsilon heavy, then the epsilon net is a hitting set. Right? So the algorithm that we will see actually will try to do that. We want to make sure that every range is epsilon heavy. And then so that when we construct the epsilon net, it does produce a valid hitting set. Right? So in order to, the construction of epsilon nets, so we also want that the size of the epsilon net is constant. It should not depend on the input size. Right? So one can design epsilon nets. So there is a beautiful theorem which we will see later, and so which guarantees, so epsilon net of small size, or not a small size, let me write it, of constant size, that depend on only
R intersection X is just R, right?
Okay, so X is the set of points. So when I say R intersection X, I mean the points lying in that range. So R is this. Because I'm not looking at a range as just a set of points.
Okay. Yeah.
So I can write it like this also, that this, that is also fine. But then what do you mean by cardinality of R would be the number of points lying in that range. So that is why I explicitly mentioned R intersection X. Okay. So epsilon net of size, this exists. So note that this epsilon net, the size is independent of the size of the input. Input family can be huge, but we can always guarantee an epsilon net of constant size, which is independent of n, provided this range space has nice combinatorial structure. And what I mean by that is, it has a small VC dimension. So now we'll spend quite some time understanding concept of VC dimension. Once we know that, then we'll see a theorem which guarantees the existence of an epsilon net of this much size, right? Provided our range space has a bounded VC dimension. Once we have that result, then we will go and design our FR.
What is VC dimension?
Yeah, so now we'll get into VC dimension. So far, this epsilon net definition, that is clear to everyone?
Can you give an example?
Example, I will give an example. Like, what is it in the definition that is not clear?
Where is in the condition?
Which condition?
R intersection X, if for all R belongs to capital R, cardinality of R intersection X, is it X or N?
Yeah.
Because
No, okay.
suddenly you are implying that R intersection N is.
Okay, let me repeat that. So you have a range space, okay? So X and X is the set of points, R is the set of ranges. Every range is a subset of X, right? It will contain points of X. Now we have set a parameter epsilon. Think of epsilon as some, say half. So we want to look at those ranges which contain at least half of the points.
Every range is a subset of X. Is that always true? I thought X was finite and ranges could be infinite.
X is finite and ranges, so I mean those ranges which are X.
But X could.
Okay, that is why I said, right? So if you're looking at the abstract set system, when there are no restriction on the ranges, think of them as subset of X. If we are in the geometric setting, so better to think of each R as a geometric object, which contains points of X. Okay, is that clear now? Is there still some doubt from the definition? So here, all I'm saying is, look at a range, look at how many points it contains from X. If it is more than, so suppose X has n number of points. If it is more than epsilon n, then we would like that this set that I am interested in, which I am calling as the epsilon net, it must intersect R. It must have at least one point that hits R. Is the definition clear now to everyone? So now let's look at this new term that has come up, this VC dimension thing. So before that, we will again need some more definitions, so a couple of ones, and then we'll get to VC dimensions. So again, I have a range space. We define something called as the projection, or it is also called as restriction. See, if at some point I use n will denote the number of elements in X, the number of points in X. Okay? So XR is a range space. The projection of a range R on, I'm taking a subset of X, so S is a subset of X. We define the projection of R on this set S like as follows. So look at every range, small r, and it intersects S. So you have this entire set X, fix a small subset of X that I am calling as S, and now restrict your ranges to this set. So look at every range in the range set and just the intersection of that range with the chosen subset. So this will be clear in the examples that I'm giving.
So
Actually, we are also online streaming it, so we'd like that you use mic before, so that people also.
So in the definition of epsilon net,
Yes.
so if for all small r belongs to capital R, there is this condition implies small r intersection n not equals phi, But the other part, small r is the cardinality of small is greater than or equal to epsilon times cardinality of x. So that's just from the condition. So that doesn't have anything to do with the definition, right? In general. So the part
Yes,
that
yes,
you
yes.
So,
So this is just a condition which ranges we want to hit. We are interested in those ranges which are heavy.
Right.
So we call this as epsilon heavy range.
okay. I was just worried about what the last implication meant, but that is just from the previous
From
condition.
the previous. So we wanted that for every range, if it is epsilon heavy, we want it to be hit.
Right.
So if my n satisfies this condition, then n is a epsilon net. So is this definition clear? The projection? Just that we are restricting our entire ranges to just a subset of the set X. Okay. And then this shattering thing shows up. So we say that a set S, again a subset of X, I'm assuming XR is a range space, I'm taking a set X. We say that this is important, this is very important because it will help in defining the VC dimension, and in fact we will see several examples how to obtain VC dimension, so this concept is very important. A set S is shattered by R See, if you look at this previous definition, the projection or restriction of R onto S, essentially what are we getting out of it? We are getting subsets of S. R intersection S is a subset of S. So now I am interested in a set such that if I look at the entire range space and its intersection with this set, if I am able to generate the entire subset, like the power set of S, then we say that that set is being shattered. Okay. So a set S is shattered by the range space if the projection of R onto S is the entire power set of S. Because we might not be, get the entire, all the subsets of S. Okay. So if we can get all the subsets of S, we say that S is being shattered by the range space. Okay, so now let's see a simple example. Say we have X is the entire real line and R is the set of intervals. And I choose a subset S. Okay. Let's say we have 3 points. So that is my set S. And now we want to see whether S can be shattered by intervals or not. Okay, we have fixed a finite subset in the entire real line. And now, given these intervals, the infinite collection of intervals, we want to see whether we can generate all possible subsets of S. We can't do it, no? So I can have an interval which does not intersect any of the 3, because we are looking at the entire family of intervals. We can have intervals just getting us the singleton sets, right? We can get AB and BC. We can get the entire thing. What we can't get is just A and C. Right? So it means that A, B and C, these 3 elements together cannot be shattered, is not shattered by the range space X comma R. Yeah? Why? Because if I look at the projection of R onto this set S, I am getting the except AC, I am getting the other subsets. Okay. What if we take just 2 elements? That will be shattered, right? So if I have another set, say T, and it consists of only 2 elements, this is clearly shattered by XR. Because plus R of t is 2k. And this motivates the definition of VC dimension. Here we will say that this range space of intervals have VC dimension equal to 2. It means that there is a set of size 2 which can be shattered, but no set of size 3 or more can be shattered. So VC dimension of a range space is the size of the largest set that can be shattered by that space. That is how we define VC dimension. Okay? So it's an important definition. This VC stands for rarely used. I don't know if I'm writing the spelling correct. These people introduced this notion, and that's why the name VC. So VC dimension of a range space
You are
is
correct.
huh?
You are correct.
Correct. So if we have a set which can be shattered, so suppose set size is k, right, and you can show that, if you can show that your range space can shatter a set of size k, then it can also shatter sets of smaller sizes. That means the VC dimension has to be at least k. But in order to upper bound it, you want to show that no, VC dimension cannot be more than k, then you have to show that you can't, the range space cannot shatter any set of size k plus 1. Okay. To prove the upper bound, you have to show the existence of some set, but for the lower bound, you have to show that no larger set can be shattered. And that is why for intervals, because we could have here, I mean, every set of 2 points will be shattered, fine, but we only need to show that there is a set of size 2 which can be shattered. But then if you take any 3 points on the real line, with just intervals, you cannot shatter them. So I hope the definition of VC dimensions, shattering, this projection, it's all clear. If there are any doubts, then now let's change the range space slightly. Let's say that instead of intervals, we have union of intervals, 2 disjoint intervals, and try to find the VC dimension for this range space. You can do it now, it won't take much time. Then we'll look at more complicated example. So X is R, we are still in one dimension, and range I am telling you is AB union CD, where A is less than B is less than C less than D, all belong to R. These are disjoint intervals. So first of all, can it shatter a set of size 3?
Yes.
Now it can. What about 4 sets? Sorry, a set of size 4. Set of size 4 can be shattered using disjoint intervals. Can you shatter a set of size 5?
No.
Why? So see, everyone can see, right? A set of size 4 can be shattered if you take union of 2 intervals, 2 disjoint intervals, which means that the VC dimension has to be at least 4. Now we want to show that it is exactly equal to 4. That is the claim. So take any set of size 5 and prove that, you have to now prove that it cannot be shattered by this. How would you show?
Take any 5 points
Okay.
and order them like 1, 2, 3, 4, 5.
Okay.
And you want to shatter So the construction goes like this. Take any 5 points
Okay.
and order them 1, 2, 3, 4, 5 from
Right.
left to right.
Hmm.
And you want to shatter, or you want to get a projection like which contains only first, third, and fifth
With alternate elements.
alternatives.
So you cannot get say 1, 3 and 5. So you have this 1, 2, 3, 4, 5 in this ordering on the real line. And now you want to see whether there is a range which can just get me the subset consisting of elements 1, 3 and 5. With just 2 intervals you can't get it. Okay, so which proves that for this range space the VC dimension is equal to, okay, just denoted by DIM, dimension of this range space is equal to 4. So in general, if you take union of k disjoint sets, just you can extend this idea to prove that the VC dimension will be 2 times k. So union of k disjoint intervals Okay, so what if we have a range space for which no matter what n I give you, you will always be able to find a set of n points which can be shattered by that range space. Suppose I give you 100 points and you are able to, your range space is able to shatter those points. Now I give you 101 points. So there is no bound on n. In that case, the VC dimension is defined to be infinity. Okay? Can you think of which range space will do that? For which the VC dimension is infinite. Font I cannot go bigger than this. When I tried. But I looked at online yesterday, it was not that small that it could not be seen. Or you can come to. Oh, that part is not visible, so I'll try to avoid writing over there. Okay. Okay. Otherwise, the font size is fine. Okay. Okay, we'll come to that example where VC dimension is indeed equal to infinity. Let's see a simpler example first. Let's say squares. Okay. Try with 1. 1 point with a range space consisting of squares can always be shattered, right? Just the intervals have VC dimension 2. 2 points can be shattered. Right? 3 points. Okay, so how to show that 3 points can be shattered? Think of some 3 points in general position so that they are not collinear or something like that. And then see whether you can get a like all possible 8 subsets using squares, by intersecting squares with these subsets. Axis parallel squares. That's important. If we allow rotation, the VC dimension actually goes, it increases. If you have points on the line, you can never get the first and the last point using the kind of ranges we are looking at, right? That suffices. Convex position, you take 3 points. Singletons are easy, right? Any 2 sets also you can do. The entire also you can do. Empty set, pick the smallest or something that does not contain any of these 3 points. Right? Okay.
We can get a construction of some of the points such that any 2 point, there exist 2 points which cannot be shattered by just a square. Because, for example, take the third point which is in above.
So suppose I have these 2 points, and where do you want me to place the third point?
Slightly above the midpoint between. Yeah.
Okay.
Now we want to shatter these two which are at the base with using a square.
So any 3 points in convex position will work. You just want to show that okay, there exist some 3 points which can be shattered by squares, which means VC dimension is at least 3. Okay, dimension here is at least 3. Now see if we, sorry.
What if we have a right hand, we have what if we have 1 point at, we have 3 points, one is at the this side of the right angle triangle, one is at this vertex and one is at the top vertex, and these have length A and A.
Yes.
Then how do
you
we
can
shatter
the
those?
2 points, I agree. So the point is you just want to say that there is a, so I think my claim was incorrect, that every point, every 3 points in convex position can be shattered, provided. So okay, here it is. Here also usually we consider points are in general position, which means that no 2 points have the same x or y coordinate. Right? So in this case, if you have points arranged like this, these 2 points happen to have the same x coordinate. So these are not the points in general position. Okay? So the claim is correct. 3 points in general position can always be shattered by squares.
Ma'am, how did we get dimensions greater than equal to 3?
Okay, so now we want to show that, okay, if you want to show that, no, this range space has a VC dimension at least 4, then you have to exhibit, again, a set of 4 points which can be shattered by squares. So you should be able to get every subset of those 4 points, 16 subsets, just by intersecting them with squares. So can you do that, is the question. If you cannot do that, then we prove that the VC dimension is 3. If you can, then VC dimension has to be at least 4. So try with 4 points. And think of, if you have 4 points in the plane, how can they be arranged in the plane? Like, assuming in general position there are essentially just 2 different configurations in which you can place the points. One where all the 4 points are in the convex position, and the other where 1 point is within the convex polygon, that the smallest convex polygon that contains the remaining 3 points. And the smallest convex polygon that contains 3 points, that is called as the convex hull. Okay, so if we have 4 points, so here we have 2 different arrangement of 4 points. On the left, the 4 points are in convex position. On the right, 1 point is contained in the convex hull of the remaining ones. So here what goes wrong? Like, which set we will not have in the projection? Just the 3 points which define the vertices of the convex hull. Right? And over here what goes wrong?
These two.
Huh?
I mean the smaller.
Okay. So
Sorry,
suppose we can shatter this set. Suppose, right? With squares. Then what we will have? We will have one square that intersects just these 2 points. We will have another square that just intersects the remaining 2 points. But then squares cannot intersect more than, 2 squares can intersect at most twice. Disjoint, or just tangent, or they actually overlap. Okay? And with the same kind of arguments you can also show, so here we have that no 4 points can be shattered, which means that the dimension has to be at most 3, and it implies that dimension is equal to 3. The same argument holds for discs as well. Discs. And both discs and squares have these properties. Every two objects can only intersect at most 2 points. So use that observation to prove that for discs also VC dimension is equal to 3. The second argument. Yes. So we want this part is clear, right? The dimension is at least 3. Now we want to show that, I mean, let's say we want to check whether 4 points can be shattered or not. Okay. So there are two possible configurations of 4 points in the plane, essentially, right? So this part is clear. If we have this, then we cannot have just the points in the convex L vertices. So consider this case. Here I am trying to prove by contradiction. Suppose this set can be shattered by squares. No. Collection of the entire range space of squares. Which means that, going by the definition, there is a square which will just give me these 2 points. It won't intersect the remaining 2. And also we have a square like this. But then, you see they are intersecting, they have to intersect at 4 points. Which is a contradiction. 2 squares cannot intersect at more than 2 points. Okay? So this shows the VC dimension for squares is at most 3. Lower bound also we have, and that means D has to be equal to 3. Clear? Allow rotations and VC dimension increases. If you don't have axis aligned squares, I think the VC dimension should be equal to 5. So, but you try it out on your own. What example should I have? Okay, so let's see this case, right? Also think about rectangles. Rectangles have, that's there in your, you'll see that problem in the problem session. So try for rectangles, axis aligned rectangles again. What is the largest, what is the VC dimension for rectangles? Think about it. And intuitively, squares are simpler objects than rectangles. So their VC dimension has to be smaller than the VC dimension of rectangles. Okay, you see here these 4 points which we showed that cannot be shattered by squares, they can indeed be shattered by rectangles. So you have a 4 set which can be shattered by rectangles. That means for rectangles VC dimension has to be at least 4. But then the other side, you try it on your own. Now say we have our range space is the set of all convex polygons in the plane. Then what happens? All convex polygons. So one can have 3 sides, 4 sides, 5 sides, whatever, bounded by finite number of sides. But how? How do you show that? So first, others also think for convex polygons, what can be the largest set which can be shattered?
So maybe we have to prove that we can shatter a regular n-sided polygon using these convex polygons for all n.
How do we show that?
I am not sure.
Yeah, the idea is fine. Okay, so I'll just tell you what goes wrong with convex polygons, or right. So you take some n number of points. So if you want to show whether we can shatter a set of n points, we don't know what the value of n is. Take some arbitrary n and arrange these n points on a circle. Okay. Now we want to see whether this point set can be shattered by convex polygons. Okay. So here I have a set with n points, and all of them are lying on a circle. Take any subset of this set. Let's say X is some subset of this set. The question is whether X belongs to the projection of R onto this set S, Sn.
Get the polygon by ordering them.
Yes. Okay. So what I have done is, see, I started with this n points. This n is some arbitrary natural number. I started with these n points, arranged them on a circle, right? And now I am taking any subset of these points. Right? The size of X is equal to k. And because, so suppose the size is equal to k, say 4 or 5, then I can have a 5-sided convex polygon from the range space which will only intersect those 5 points. It won't intersect the remaining points. Right? So I have these 5 points and I can intersect them with a 5-sided convex polygon. So this argument shows that no matter what subset I have of Sn, we can always have a range which will only intersect the selected set. Right? So Sn can be shattered, and this n you can make arbitrarily large, which means that the VC dimension here, it is not bounded. It's infinity. Clear? Okay. Now what if we restrict these convex polygons to be bounded by, say, k sides? So now you have polygons which contains, which are bounded by collection of k-sided polygons. So now you have to try it hard. It is no, not k plus 1. It will come out to be 2k plus 1. Okay. So again, take an arrangement of 2k plus 1 points on the circle and try to prove that every subset can be there in the projection.
And an arrangement of 2k plus 2
That is easy. 2k plus 2 points, then you take the alternate points and show that it cannot be shattered by a k-sided polygon. So you have say 2k plus 2 points on the circle. Take the alternate ones. How many are there? K plus 1. You cannot shatter them by a k-sided polygon.
But what is the clean argument for that?
For what part?
If you take that k plus 1 alternate points, you cannot shatter them by a k-sided polygon.
I think that is enough to just, we have a k-sided polygon and it is a convex polygon. If it contains k plus 1 point, it has to contain some other point as well, the neighboring point as well. Right? So, I think now I'll just quickly do one more example and just, then we will get to the algorithm part. So can you quickly tell me if we have half spaces, half planes in R2, say in R2 we have half planes, what will be the VC dimension? I won't do it here, just think. VC dimension for half planes. Can you shadow 3 points? Okay. 3 again, general position. Okay. And what about 4 points? Same problem arises. You want to just get these 2 points, but any half plane that contains 2 points will also have to contain the other point. And there is a theorem called as Radon's theorem. I wanted to do a proof also, but I'll just state the theorem, and it will imply the VC dimension for half spaces in D dimension. So what it states is, if I have, say I have a collection of D plus 2 points, in D, yes, in RD, then we can, there exists a partition so we are partitioning this set into two parts such that if I consider the convex combination or the convex hull of A and the convex hull of B, they must intersect. Do you see this in 2D? Suppose I have 4 points and these 4 points are in general position. Then there always exists a partition of these 4 points into two sets such that if you take the convex hulls of these two sets, they will always intersect. So on the board itself, so here say I have these 4 points, right? So one convex hull is this, other is this, they intersect. Here also you take the convex hull of these two, convex hull of these two, they intersect. And one can prove it in any dimension D, provided we have D plus 2 points. Okay? And with this result, what we can show is that for half spaces, the VC dimension has to be, it cannot shatter a set of size D plus 2, it has to be at most D plus 1. And the lower bound side, you take D plus 1 affinely independent points, they can be shattered. And which will give you that the VC dimension is D plus 1. Okay, so that's it for the VC dimension thing. I hope we did enough examples so that this concept is clear. So, if there are questions we can take, then I'll move to the epsilon next part. Good? Okay. So we had this epsilon net. The definition is clear to all. Now we have this theorem which says that if I have a range space of VC dimension, some constant, bounded VC dimension, not ranges like convex polygons. Right? So any range space of bounded VC dimension, so say of VC dimension equal to D or at most D, then there exists a random sample of size D over epsilon log 1 by epsilon plus 1 by epsilon log 1 over delta, which is then there exists a random sample of size this, which is an epsilon net for the range space with probability at least 1 minus delta. So you pick a random sample of this size and you can prove that with some positive probability the resulting random sample is indeed an epsilon net. So look, this is a, so later there was Matusek, he gave it's a very nice paper, he gave a construction, a deterministic construction for epsilon nets. So I will state that result as well. So anywhere if you have an algorithm which uses epsilon nets, and there is another concept called as epsilon samples, one can, if one restricts to random samples, then you have a randomized algorithm. But if you look at the construction of, if you use the construction of Matusek, the deterministic construction, and that's the only part in your algorithm which is making this randomized decision, then you have a deterministic algorithm. So a deterministic epsilon nets, and this is by and he gives a result that again XR is range space of VC dimension D then an epsilon net of size. So here we can simplify this expression, right? This delta is some constant. Yes, yes.
So can you explain this epsilon net theorem? I mean,
Just give an idea I can give, but the proof itself
no,
takes
not
some
the
time.
proof, but what the statement means, as in,
so what the statement of this epsilon net theorem means, as in, from how did we get into probabilities? I mean, what is the underlying probability space, or I mean, what is random about this sample?
We are picking points uniformly at random from the set X.
Alright.
Okay, so this X has some finite size, say n. You are picking points from the set X uniformly at random, and the claim is that if you pick enough number of points, that will be an epsilon net for the range space.
So
without
replacement.
Without replacement.
Oh.
Or with replacement, maybe. With replacement also, we can prove that it is an epsilon net.
Okay. Also, the part where there exists a random sample with probability. So when you say there exists, so is it random anymore?
Okay, I should write it better. So an epsilon.
Or for every random sample, this is the probability.
Uniformly random.
Then yes.
You mean
I mean,
there is a
it is
distribution?
actually, huh?
So you mean that there is a distribution from which if you draw a random sample, you get a...
The only requirement is that it has to be of sufficient size. And we can prove that it will
So
be an
you should
epsilon.
be then any uniform random sample maybe of this size.
Actually, yes. Then any uniform random sample of that size is an epsilon net for the range.
With this probability.
So distribution doesn't matter.
No, that's uniform distribution.
We are assuming
You
here
are picking points.
points that.
So thank you for the
So that should be omega, right?
Which one?
O
No, of
size more than
yes, so theta. You in near linear time. So what is it? R square log. So there is a construction that is known, which can get you an epsilon net in near linear time. Okay, once we have this result, so can we define epsilon nets for weighted range space? If every point has a weight, additionally it also has a weight. Then also you can define which ranges are epsilon heavy. So you look at all the points in that range, sum up their weights, and look at the entire set, that what is the total weight. So if the weight of this range is at least epsilon times the total weight, you must hit it. Right, so that is the epsilon net in the weighted setting. Okay, so now we get into this. We want to design an algorithm for hitting set for ranges or range spaces with bounded VC dimension. And this construction given by Matusek, it also works in the weighted settings. Right? So we can invoke this whenever we want to find an epsilon net. Okay? Okay? So say we have our input is the range space and VC dimension D. it must have some hitting set, an optimal hitting set also. So let's say that H is an optimal hitting set. So size of H is okay. Now the main idea behind the algorithm is this. What we want to do is we want to assign weights to the points in such a way that the points which are in some optimal set, they get a lot of weight and the remaining points get less weight. Why is that going to work? If I pick any optimal hitting set, it must hit every range, right? If we can somehow ensure that these points have large weight, what would that imply? Those ranges also become heavy. And if every range becomes heavy, then the epsilon net will be a hitting set. So initially whatever we are given, the range space, there are no weights. Now we want to assign weights and update them in such a way that every range becomes heavy, so that once you invoke the epsilon net, once you find the epsilon net, that is guaranteed to be the hitting set for the range space. That's the main idea. You can do a thought experiment here also. So suppose I can assign weights like this, right? So say I assign a weight of 1 to every x in the optimal hitting set. There can be many, and 0 to others. Okay. So in this case, what is the weight of the optimal set? OPT. Okay. And if I look at any range in my range space for any arc, what is its weight going to be? It has to be at least what? Lower bound. At least 1, because there must be at least one point in H which is lying in this range. So this has to be at least 1. So what epsilon must I choose so that the epsilon net is a hitting set? What should be the value of epsilon? 1 over? I'm lost now. No, the question is, so suppose we assign weights like this. We don't know what the set is. Say we are doing some thought experiment here. Say the weights are assigned like this. Then we know that the optimal hitting set or any optimal hitting set will have weight at least equal to OPT. Any range, because it is hit by a point in the hitting set, it will have weight at least 1. So my question is, for what value of epsilon, how should we set the parameter epsilon so that the epsilon net is a hitting set, becomes a hitting set? 1 by size of H, 1 over OPT, right? So for epsilon is equal to 1 over OPT, the epsilon net is a hitting set. Okay, now the question is, okay, good, weights exist, good weights exist, but how do we find them? That is the question. And that is what the algorithm will try to do. So it's a simple algorithm, the analysis is a bit. Can someone suggest the algorithm? So you are given a range space. We want to assign weights to the points. Enough weight so that optimal set receives a lot of weight in comparison to the remaining points. So it's an iterative algorithm. We will start with uniform weight and then update the weights as in every iteration. So see what we do is, you start with, okay, let me just say set the weight of every point to be equal to 1 for every x in x. How much time time do we have? 10 minutes more I'll take, and then I won't be in hurry, and I can explain it nicely. So set this weight to be equal to 1, okay, and before this we will assume we know OPT, which is not a, okay, we'll see how to assume or find OPT, guess OPT. Is constant in the, I'm setting epsilon to be 1 over 2 times OPT, just to make the calculation simpler. Okay. And now I find an epsilon net. For this epsilon with weights equal to 1, I find an epsilon net for the range space. What will be the size of the epsilon net? What is the size of the epsilon net? 1 by epsilon, log 1 by epsilon, right? Order. And what is 1 over epsilon? OPT, right? Order OPT. So what does it give? If this epsilon net n happens to be the hitting set, then I am getting a hitting set of this size. Then what is the approximation factor? Log OPT. Okay. So if n, like return n, just you stop if n is a hitting set. If it is not, then if it is not, then what can we say? There is a range which has not been hit. And why the range is not hit? Because it was not heavy enough. Okay, so there exists a range R in R such that the weight of this range, okay, weight of range is less than epsilon times the entire weight of x, or I can simply say that this range is not hit, such that R intersection n is empty, and for all the points in this range we'll double the weights. So you double the weight of all points in this range in R intersection x. And repeat the process. So let's repeat this. That's the algorithm. That is what we have to show. Okay? But the algorithm is clear?
Could you please repeat the
yes. So we are, okay, so I am guessing the value of OPT. Right? So you guess some value of OPT. And set epsilon to be 1 over 2 times OPT. Okay? Epsilon is set. Now what you do is, you assign a weight equal to 1 or some like same weight to all the points. Okay? Find an epsilon net, which I am calling as n. If n happens to hit every set, we are done. That's the hitting set. Okay, and by the epsilon net theorem and the later constructions, we know that the size of the epsilon net is 1 by epsilon log 1 over epsilon. Okay, if it is not a hitting set, it means that some range is not hit. Okay, and for those, if there is a range which is not hit, that means it is light range, it's not epsilon heavy, we'll double the weight of all the points in this set and repeat the process. That's the algorithm. And you can see it runs in polynomial time. We have to do it multiple times because we don't know the value of OPT. You might have seen such algorithms where you assume the value of OPT and then run it multiple times. Right? So what is not clear is whether it will terminate or not. Okay? So we want to say, we want to bound the number of iterations. So let's say that the algorithm runs for k times. Now, initially I had n points and every point had weight equal to 1. So what was the total weight? N. In each iteration, how much is the weight increasing? Weight of the entire point set? See carefully. We are only increasing weights of points in a light range. that means
less than epsilon times gamma dx.
that means the range has weight, total weight is less than epsilon times n, right? So the weight increases by a factor of 1 plus epsilon in every iteration. If we run it for k iterations, after this, after k iteration, the weight of the entire set will be at least 1 plus epsilon to the power k, and the initial weight was equal to n at most. Because in every iteration I am just picking a light range, and its weight is less than or equal to epsilon times the weight. So this can be simplified to 2 to the epsilon k, or 1 plus x is less than or equal to e to the x. So e to the epsilon k times n. Okay. Now let's look at what happens to the OPT. Fixing one OPT, what happens to the weight of this? What can we say about this? Like in every iteration, can we guarantee that at least one point in the heating set is its weight is getting doubled? Why?
Otherwise it will be a heating set.
Otherwise?
If there is no range, okay.
It would already be a heating set.
So claim is, we want to say that this heating set, if I look at any iteration, there is at least one point in this set whose weight will definitely get doubled. Why this holds? Why this is true?
If the heating set was already hit, then you just return it. Otherwise, you are doubling the weight of all non-hit points.
Not all non-hit points. So first of all, it does not make sense to say the points are not hit. What we are hitting is the ranges, right? And we are only doubling the weights of points in one light range, not all the light ranges. Just existence of one light range, pick that set and double the weights. That's it. But why it is guaranteed that in every iteration at least one point in set H will have the weight doubled.
Because H should contain at least one point in
H must contain at least one point in R, right? H is a heating set for the entire range space. So when we are doubling the weights of all the points in the set R, at least one point in H must have its weight doubled. So let's say that if I fix a point small h in H, let's say that its weight gets doubled some number of times. Let me denote that by ZH. Then the weight of H at the end of k iteration will be what? I sum it over all the H. That will be the weight of the optimal heating set. Right? Fix one point in the optimal set. See how many times it is being doubled. Okay. So the total weight that this optimal set will receive at the end of k iterations will be at least this. Right? And now what do we do? Now we have to do just some math. Okay? And you can show that this constant here, 2 epsilon, what is the value of this? 1 over OPT. The size of H is also OPT. That means we have some parameters which sum up to 1. Jensen's inequality can be invoked. Okay, and so I don't know, I don't have time to do all the calculations. I just take a look at my note and write the final thing here. So this comes out to be 2 to the 2 epsilon k over 2 epsilon, right? And the last thing that we need to do is just see how do these two, what is the relation between these two weights? H is a subset of x, right? So this weight cannot exceed the total weight. So weight of H is upper bounded by the weight of x. Just substitute these and rearrange the terms. You can upper bound k by so k is 3 2 over epsilon log 2 n epsilon. So indeed this terminates. So what we do is, so the only missing thing is how to guess OPT. Start with value equal to 1. Set OPT to be equal to 1. Epsilon is equal to half. Run this algorithm for how many iterations? K iterations. If it returns a hitting set, good. Otherwise, it means that our estimate was an underestimate of the optimal hitting set size. Double it. Run it again. Okay. So at any point when it stops, the epsilon net size is this, and therefore we will be guaranteed that we finally get a log OPT approximation happen. That's it.
Why do we double the weight of those points?
That works. So we have seen like other algorithms where you just not double but square also. You have to see what works. It works.
So when we choose n, how do we choose n?
Which n? N is the number of points.
No, capital N.
Capital
like epsilon net for.
Oh, I wrote one. So Matusek, he has given an algorithm to find an epsilon net. It's a deterministic algorithm. Otherwise, you can the random sample of that size is guaranteed to be n.
So we are assuming that the VC dimension is an input.
VC dimension. Oh, we are given the range space.
And the VC dimension.
We know it. I mean, once we know the range space, we know the VC dimension. That is what we did. So, okay, I mean, we did it in an ad hoc way, right? For squares, we actually came up with 3 points and 4 points cannot be shattered and things like that. But there are theorems which say that if you have objects whose boundary you can write it as a polynomial, its VC dimension is bounded. So there are many theorems which guarantees that many objects, many ranges, they have bounded VC dimension, they behave nicely.
Bounded is fine, but it's exact.
No, not exact. We can say that VC dimension is at most D. No, exact value is not needed. Unless it's an upper bound.
Finding VC dimension, is it NP hard?
No. Is it NP hard?
We can take other questions.
Yeah. Thank you all.
We will have lunch now and we'll meet again at 2:50. So if anyone has more questions, so they can.
Can you explain these two calculations?
So this, in every iteration, the rate of x is increasing by 1% in factor.
That is fine.
Right. So after k, we will have total weight bounded by this.
And n because
N is the initial weight. So I have this x is of size n, and initially I'm setting